effect.
All right. So let me start. So what is photoelectric effect? So it is the phenomenon of emission of electrons due to the incident photons, right?
Yes, sir.
And electrons thus emitted are called photoelectrons. Okay. And current developed by emitted photoelectrons is called photocurrent. Okay. So generally, this was the effect which was studied in the discharge tube experiment, or you can say during the discharge tube experiment. So in a discharge tube experiment, what we know? So it's a transparent glass tube, right?
Yes, sir.
So we have two electrodes. One of them we call cathode and other we call anode, right?
Yes, sir.
So cathode means it is going to be connected across a negative terminal of the battery or the power supply. So generally, one of the plate is having the lower potential, which we call cathode. Cathode means the negatively potential, plate, and the high potential we call anode. So what really matters is low and high. It's not positive or negative. So what really matters is low and high. Okay.
Yes, sir.
So if the negative is, let's say, -10 and positive is -5, so it's still cathode and anode. So respectively, so this is your cathode. This is your anode. And because of this polarity, when we suck the air out of this discharge tube, when it is close to vacuum, because we cannot create the absolute vacuum, but it is close to vacuum, when the pressure drops to maybe the fourth place of decimal in atmospheric pressure, maybe 0.0001 atm. So when the the gas density is really low, in such case the field produced between the plates, because the field will be from where to where? From the plus to the minus, right?
Yes, sir.
So this is the field between the plates. And now we create an kind of window in the glass tube. So let me remove this part. And let's introduce a window. So window is like a, a transparent part. It is generally the entire tube is transparent, but still we have a thin glass so that the absorption is less. And that is actually needed for the allowing the photons to enter the plate. I mean the tube. So now photons can enter here.
Sir, absorption where?
By the glass itself. Every medium can absorb energy, isn't it?
Yes, sir.
If it is coming through this thickness will absorb, right?
Yes, sir.
So we want to make it thin someplace so that it can enter mostly from there. So it is like a window.
Yes, sir.
Sometimes the glass tube may be having some colored glasses used. So if it is colored glass, then the light will not enter. So we have some transparent glass which is of no color, which is like a colorless glass, so that the maximum light can enter and hit the cathode plate directly. Now,
Okay.
what is the essence of this experiment? The essence is that it is not necessary that every, if I connect an emitter here, so it was found that every photon is not capable of ejecting electrons, because if it is ejecting electrons, then what will happen? The moment you will eject some electron, this field which is on the left side will apply force on the right, right?
Yes, sir.
Because the charge is negative, so force will be on the right, isn't it?
Yes, sir.
And this force will accelerate the electron. And therefore, if electron is there, it will accelerate and eventually reach the anode, isn't it?
Yes, sir.
And if it is going to reach the anode, then some current will be detected, isn't it?
Yes, sir.
So if current is going to be detected, then definitely we can detect the current. And so you can say that a photon has emitted the electrons, but it is not found in every case. Okay. So every photon is not capable of ejecting electron. So what is happening here? Why every photon is not capable? So even if you wait for some time, keeping the same radiation of fixed frequency, if you have the fixed frequency, if you keep this as constant, unless the frequency will not exceed some threshold value, photoelectrons is not observed. Okay.
Yes, sir.
Now the question is why photoelectrons are not observed for a given frequency unless we are not exceeding certain value. So the answer is if light is a wave, then wave can be absorbed by the medium, by the surface. And if light is like a wave, then the surface of cathode keep on absorbing the energy. And once the energy will exceed some value, it should have started ejecting electrons, but it is not something which was found in actual experiment, which was the clear indication that light is not like a wave. Particularly in this case, the behavior of light is not like a wave, rather like a discrete particle. Now, particle in a sense of light is not like a physical particle. Particle is a term which was coined by Einstein to represent a localized form of energy. In a way, energy which is propagating in form of a small packet. The packet term in Greek we call quanta. And the photon is called the quantum of light, or you can say packet of light. Now, every packet should be capable of ejecting the electron. If it is not capable, then no matter how many packets are coming to you, it will never let you enter it. So it is like, let's say, if there is a some sort of automatic vending machine which can dispense stuff only when it will receive certain fixed amount. So let's say if you have to insert 10 rupee coin, it is like a device which can only function with 10 rupee coin. So if you give 5 rupee, even 2 times, it will not deliver the item. It should receive that amount at once. Then only it will show some effect. It will dispense the object which is intended. So similarly, the photon coming as a packet is having certain definite energy. And when that definite energy exceed a threshold value, it is capable of ejecting electron. So it is like a imagine a situation when we have a some sort of one-to-one interaction. Let's say if you go and interact, if a photon is capable of interacting with only one electrons at a time, so when it will reach the electron, it will interact based on the energy value. So if energy value is not sufficient, it will reflect back and the electron will remain there. When the next photon will arrive, it will do the same thing and will go back. When third will arrive, it will do the same thing and will go back. But if the fourth photon coming is having sufficient energy, then it will knock out that electron and will show the photoelectric effect. So photoelectric effect was basically manifestation of the particle behavior of light. The particle behavior means a localized energy behavior. So photons are supposed to be carrying a definite amount of energy, and this definite amount of energy is going to interact with one electron at a time. No two photons can interact with the same electron at one time. So maybe because of the dimension, the nature doesn't support such interaction. So photon interaction with electron is supposed to be 1:1. It cannot be many to one relation. It is always 1:1 relation. So that is why a single electron is ejected or not depends on interaction with single photon itself. Because at one time you can only interact with one photon. So either you will be ejected or you will be not. So in that case, the photon is said to be reflected back. So in such case, the photon is not going to, it is said, okay, it is not interacting, it is returning back. But if you go by the classical theory of light, which talks about the light as a wave, in that case, a wave is a continuous flow of energy, unlike the discrete behavior that I discussed. And if the wave is continuous flow of energy, it means you can keep on absorbing. So if something is continuous, then eventually it will exceed the desired value. And so the photoelectric emission should take place. But it is found to be contrary to the experimental evidence that the continuous flow of photon never been able to eject electron unless it is not crossing certain frequency value or unless it is not below certain wavelength value. It's the same way of saying the same thing. So what really matter here is the frequency, not the intensity. Here the word intensity is used in the context of amount of photons received by the plate per unit area and per unit time. Okay. So no matter whether you increase the the flow rate, let's say if I give you 10 photons per second and then I start giving you 20 photons per second, now then I start giving you 30 photons per second, unless I'm not increasing the energy value, you're still interacting with the same energy photon. And because if one is not capable of ejecting, then no matter how many will come and go, they will never eject any photoelectrons. Understood what I'm saying?
Yes, sir.
So to eject photoelectron, one thing is clear that the classical idea will not be followed. If classical idea is believed to be followed, then it should have eventually emit the photoelectrons after absorbing sufficient energy. But the energy is not getting absorbed by the surface, rather the photons are coming, and these photons are not only interacting with the electrons, but these photons are also interacting with the atoms at the lattice points. Sometimes that energy is taken by the atoms and they do excite the kernel electrons. They do use that energy to vibrate, which in turn changes the temperature of the system. But when it comes to the ejection of photons, photoelectrons, then the photon is supposed to interact with one electron, because the interaction is 1:1, which means only one can interact at once with only one electron. So their interaction must be in a way which is energy wise, you can say, feasible, or energy wise sufficient to overcome the bond of the electron from the metal surface. So this is the minimum energy which we need to remove the most loosely bounded electron from the metal surface. We call threshold energy. The term is also known as work function. So there's a term that that has been coined, which is called work function, which means it is the minimum actually work done by the, you can say, by the incoming photons, which is carrying sufficient energy to overcome the interaction between the electron and the surface of the metal. So basically, why we are studying photoelectric effect? This is a clear demonstration of the particle behavior of light. Now, de Broglie, or you can say de Broglie, he got the Nobel Prize for showing that the particle can behave as a wave. So matter can behave as a wave. Okay. We have other effect in which is if matter can behave as wave, the wave should also behave as a matter, right? So if light is when it was earlier assumed to be wave, and the wave-like character was kind of most prominent thing, but the world was kind of divided into two proponents. One was favoring the particle behavior of light, another was favoring the wave behavior of light. And this controversy existed for a very long time until the Einstein gave a dual nature of light proponent, that okay, light can behave as both depending on the situation. So photoelectric effect is one of the most you can say powerful experiment which actually manifested the world that light is indeed behaving as a wave, because the interaction is only possible when one single photon can eject. It is not the number of photons received by the surface, rather it is the amount of energy carried by one single photon which will matter. And if that energy is sufficient to eject, it will eject. And if that is not sufficient, it will never eject. Understood?
Yes, sir.
So that was the purpose of photoelectric effect. The purpose was simply to understand the particle behavior. And that is what we are studying here. So here we define certain things like certain terminology which we should be aware of. So we should know something called the work function. It is also, you can think as a threshold energy. So work function of threshold energy. Now, what is this work function? So let's say, imagine we have some cathode plate. So let me draw this cathode plate. So now we have a cathode plate, and what is happening? This cathode plate will try to, and let's say it is receiving some photon, and this will try to eject the electron. So now the plate is electrically neutral, but the moment this electron will try to jump away, the plate will actually develop a positive charge. right?
Yes, sir.
The electrical neutrality is going to be disturbed. So a
Yes, sir.
slightest movement of electron will have the opposite polarity develop on the plate, and therefore an attraction will start exist between the two. So this attractive force, if it is sufficient, then the electron will come back. Okay. So to get rid of this attractive force, you need to go really some distance away. That distance may be in micrometer, maybe in maybe nanometer also, but it is in some value beyond which they cannot interact. Now, to overcome this attractive force, you need to have sufficient kinetic energy. Okay, you need to have sufficient energy which can let you go away from this attraction. And this energy which you need to overcome this attractive force, this energy for the most loosely bounded electron, we call the work function. So work function is the energy which you try to, when you try to escape the metal surface. See, these electrons are free electrons. They are not bound to the atoms, but they are bound to the lattice. Okay. So someone which is bound to the lattice, but not to the atom, are free electrons. They are connecting electrons mostly. When they receive photon, when they receive the energy in the electromagnetic waveform, they try to escape, but the moment they try to escape, they feel the attraction because of the disturbed neutrality of the lattice, and this attraction needs to be overcome in order to escape. And that energy we define as the work function, or you can say the threshold energy. So here you can define, there is a definition which one should remember. And what is the definition?
So it is a minimum energy that is required by a free electron to
Yeah,
escape from the metal surface.
yeah, it is like the most loosely, like the topmost layer of the metal surface. Because what is surface? If you remember from in other chapters, I have discussed the surface in electrostatics as well. A surface is not the top layer. A surface in the language of physics is the top 5 to 10 atomic layer. Okay.
Yes, sir.
So when I use the word surface, I always talk about the layers. Okay. So what is surface? The first 5 to 10 atomic layers. So the first 5 to 10 atomic layers is called surface. Now among that surface, we have different layers. So it is not necessary that every electron will come from the top layer. You may hit the electron in some deeper layer also, right? And
Yes, sir.
in that case, the electron will be free from the layer attraction. Okay, because the attraction will exist for only few layer away. But again, the other top layers may, under which you will undergo some collision with the atoms, with other electrons, and you may still remain inside the metal. So every electron is not capable of escaping, even though they have received sufficient energy from the photon. So when you receive energy from photon, it is not necessary that you will leave the surface eventually. You will leave your own layer of surface for sure. But whether you will leave the metal as a whole, that's a questionable thing. So that depends on the, you can say, kind of probabilistic. This is the probabilistic nature. And that is why, even though a metal surface is receiving photon more than threshold, only a fraction of photon is actually enabling the photoelectrons ejection. What does it mean? It is quite possible that out of 10 photon, one is reaching the top layer, but other 9 are reaching the other deeper layer. So their ejection is not converting into photoelectrons. Their ejection is, of course, overcoming the work function of their respective layer, but still that energy is not sufficient to let you eventually come out of all the layers. So when we define the work function, we only talk about the most loosely bounded, which means probably the layer top of the surface, because surface itself is having many layers, right?
Yes, sir.
So let's say if you have sufficient energy to escape your home, so you have a fare to pay for the taxi to reach the airport, but if you don't have the airport ticket, you can't leave the country, right? So sometimes you are free from the home, but you are not free from the city. So you need some more energy to, board a train or a flight. Let's say you are in an island and there is only one cruise which takes you out of the island. So you may reach the edge of the island. You may reach the you can say the pier of the where you can catch the cruise or the port area. But still that is not sufficient, because there you need some more energy to buy the ticket and take the cruise, right? So if you reach
Yes,
the edge, but that will not guarantee that you will come out of the island. So you're still stuck in the island, right? So
yes, sir.
maybe, I mean, when you throw something out of a denser, region, it may, hit some other layers and still remain confined within the layer. So every electron is not capable of ejecting the electrons. Eventually, some are capable, and therefore we define something called the quantum efficiency, that compared to the number of photons received by the cathode, how many photoelectrons is capable of ejecting. Quantum efficiency is definitely going to be a fraction. Generally, it's a very small fraction. It may be 1% or maybe 0.5%, maybe 0.75%. So out of 100 or out of 200 photons, just one is creating this effect. It doesn't mean they're not able to remove the electron, but they're not able to remove from the metal as a whole, from the object as a whole, from the cathode as a whole. So work function is defining the energy required to remove the you can say the least energy required electron to go out of this metal surface. So we say that it is the minimum.
So like even within these 5 to 10 atomic layers, if it goes to like I don't
Yeah,
know, maybe like the fifth atomic layer, still there is like no guarantee that the
no
electron
guarantee.
will escape.
No, there is no guarantee. That's why we define something called KE max. What is the maximum kinetic energy possible? These all are possibilities. These are like kind of a probabilistic study about the behavior. It is not the exact behavior. So we have a guess, hit and trial kind of thing. Okay. So it is the minimum amount of energy required to remove the most loosely bounded electron from the metal surface. Now, one thing is clear, that it is energy generally required to overcome the attractive force of the layer. So you may leave your layer, go to the next layer, or next layer you will make some collision, and eventually you will lose your extra energy, and then you will remain confined within the lattice. Okay.
Mm. Yes, sir.
So there is a question. So this is the threshold energy. So there is a question, something called cutoff frequency, or also called the threshold frequency. So we can write a new cut or new TH for threshold, because the work function we define by the symbol phi, and phi represents energy actually. Okay.
Okay.
So phi is like a null vector, right? So
Yes, sir.
null means you have nothing. Nothing means nothing kinetic energy. If you give only this much energy, then for sure you cannot have extra energy, right?
Yes,
So
sir.
phi, if I equate phi with some photon energy, h nu, then this nu is called the threshold frequency. So how to find the cutoff frequency? Phi by h. Very simple.
Yes, sir.
We have cutoff wavelength lambda th. So what is cutoff wavelength? It is the, now this is the minimum frequency that can create the photoelectric effect. This is the minimum frequency that can create the photoelectric effect. If frequency goes below this, then we cannot expect any photoelectric effect. Is this clear?
Yes, sir.
Okay. So what is cutoff wavelength?
So
So
it
if
is the
you,
maximum wavelength.
yeah, so it is the, so the cutoff wavelength is SC by phi, and this is the maximum wavelength which can create the photoelectric effect. Anything more than this will do nothing.
Yes, sir.
Okay. So that is how you can define the cutoff wavelength and cutoff frequency, which is commonly asked in the examination. So now the question is it sufficient to remove the electron from the metal surface by giving this much energy? The answer is no. Because it will not guarantee that it will leave the all layers, right? It may leave the layer at which the photon, because see, every wave will have some penetration power. So every photon is not need to hit the top layer. It may hit the next layer or next layer or next layer and so on. So generally, even the visible light will have some penetration power. And this is what I discussed in the solar cell, if you remember, right? That
Yes, sir.
higher frequency or the lower wavelength can penetrate deeper into the surface. And because we wanted to hit the photons in the PN junction depletion region, so we kept the top layer, the p-type really thin, so that the photons can penetrate the p-type and reach the depletion, where the electron hole pair can generate, and that can be pulled back by the substrate to create the potential difference, which we can derive for power consumption, right?
Yes, sir.
So that what I discussed. Similarly here, even the visible light will have some penetration power, and therefore every photon, by the nature of probability, will not hit the same layer. So when they enter the deeper layer, and when they have even sufficient energy, let's say more than threshold, they eject electrons from that layer, and that electron will have some extra energy called the kinetic energy. And with that kinetic energy, they try to escape, but again, due to the interatomic or inter-electron collision, even that kinetic energy is lost. So eventually they don't come out. So Einstein gave the relation. We have the Einstein
Sir?
photoelectric equation. Yes, you would ask something?
Yes, sir. Sir, I don't understand like about the penetration part of a photon? Like, how does it do that? I mean, like when it interacts with an electron, then automatically the electron will come out. I mean, given that the photon has enough energy.
Just a minute.
Okay.
Just a minute. Okay. First of all, you need to understand that a metal will have a lattice shape. So there is a interatomic gap, right?
Yes, huh?
So when I say layer, then I say atomic layers, right? So for
Yeah.
human eye, it is like a solid object. There is no gap, but for photon, there is a sufficient gap. They can enter different layers. Okay. So
Yes, huh?
it is not necessary that every photon will only hit the top layer. It can enter, it can hit the electrons in the second layer or third layer and so on. So the penetration means you can go deeper into the layer, and which is the property of any photon. Okay.
Okay, sir. Sir, so this penetration part, it is like due to the nature of the wave. Like if it is like, I don't know, having a very high amplitude, then there is a
See,
probability that it would again hit in the.
I will tell you something. First of
Yes, sir.
all, this particle is not like a physical particle. It is still a wave, but it is called the confined wave. Imagine water coming out of tap. What do you think? Water coming out of tap is what? It's a continuous flow or it's a discrete flow? Tell me.
Sir, nearly continuous.
Now imagine during the Holi, we fill the water in a balloon and we throw. The same water is in which flow? Continuous or discrete flow?
Sir, discrete, sir.
So when you have confined water, although very small amount, which is continuous in its volume, right? So if you look within the balloon, it's continuous, right?
Yes, sir.
But balloon is giving some sort of boundary to it. Okay. So this
Yes, sir.
continuous liquid is kind of confined. So this confinement we term as particle nature. But within the balloon, what we have? Within the balloon itself, we have again continuous thing, which is water. So a photon is a collection of wave, but this wave collection will be confined within very small volume, beyond your imagination, definitely, beyond our imagination, for sure. So this confinement of energy, although it is in the wave form, but it is confined in a tiny volume. This confined nature of energy we term as particle. That is the definition of particle in the world of, you can say, in the words of Einstein. So here the particle should not be confused with your day-to-day life experience of particle. It is neither the granular particles of sand or some powder or some soil or rock. It is not that way. So you need to develop a new intuition of particle. The word particle should mean something different in this case than your regular perception of particle. Understood what I am saying?
Yes, sir.
So what is particle here? It is
Sir,
still a wave, but confined within a very tiny space. And this confinement of energy, of course, it's a continuous flow of energy. It's a wave energy, but because of the confinement, we term as particle. A particle behavior actually mean the confined energy behavior. So the example of water in a balloon and a water in a tap is analogous to the particle and the wave behavior of the same water. So of course, water in the ocean, river, lake, wherever there is a flow, it is continuous flow, isn't it?
Yes, sir.
But if I make a tiny packets of water balloon, if I start throwing, although it is continuous, but still it is discrete, isn't it?
Yes, sir.
So the particle meaning is quite different from your regular perception of particle. I hope this is clear to you.
Yes, sir.
So because it is eventually a wave, it will have some penetration power. It will have some wavelength.
Yes, sir.
So if the wavelength is really small, it can go deeper into the layer in the crystal.
So at that point, why so?
Because if let's say you are a rat, so you can enter any building, right?
Yes, sir.
Imagine you go to parking space where you see lots of pillars, right? Do you see the pillars?
Yes,
But
sir.
across the pillar you can still move around, isn't it?
Yes, sir.
Because of your small size, isn't it?
Yes, sir.
But imagine a large elephant. So the elephant cannot enter the parking space, isn't it?
Yes, sir.
So the same space is not penetrable for the elephant, but it is penetrable for the humans, for the cars.
Yes, sir.
But is it penetrable for the trucks,
No, sir.
for Volvos?
Yes, sir.
For Volvo truck. Okay, sorry.
Then no, sir.
No. So the penetration simply means if size is allowing you to go deeper, you can go deeper. Understood?
Yes, sir.
So smaller the wavelength, it can have more penetration power.
Okay, sir.
Okay.
Yes, sir.
So now the penetration is a common sense. I mean, everyone should understand the penetration means can you go deeper? So if your size were low, you can go deeper. Let's say if a person is blindfolded and if I leave the person to run in the parking area, he may hit the beam also, right?
Yes, sir.
Or he may keep on running between the two beams for longer distance till he hits the wall or some other end. So randomness will make sure that all photons will not go in one direction. So all can hit different layers, isn't it?
Yes, sir.
So that's why every photon will have a different penetration power. Or the probability it will hit different layers. You can say there's the equal probability it can hit every possible layer in the surface. Definitely,
Yes, sir.
the deeper surface will have slightly lesser probability, but the outer surface will have more probability, right?
Yes, sir.
So when these photons will reach those layers and will pick one of the electrons in that layer, it will give the energy to the electrons. Electrons will come out of the layers attraction. But while coming out of the process, while coming out, it may hit other electrons or the lattice points and eventually get confined there only. So all of the energy it will lose in the due process of collision, right?
Yes, sir.
It is possible. I'm not saying it will do every time, but there is a possibility it can lose, right?
Yes, sir.
So what Einstein said that when you give energy to any electron, and if this is more than 5, this difference of energy is called Q value. Okay. What do you call? Q
Q
value.
value.
Now, the kinetic energy is not the Q value. The kinetic energy is what we eventually receive when those electrons come out of the metal surface completely. So when you come out, the kinetic energy of the ejected photoelectrons. See, when I say photoelectrons, when they come out of the metal, we call photoelectrons. When they are still trapped within the surface, we don't call photoelectrons. When we say, when they come out of it. So when photoelectrons are emitted, then the kinetic energy will be either equals to or less than Q value.
Yes, sir.
So is it necessary that it must be equal? It may be
No,
zero
sir.
also, right? So it
Yes,
could
sir.
be zero as well. So kinetic energy of ejected photoelectrons can lie from where to where?
From 0 to the Q value.
It could be anywhere between 0 to Q value, right?
Yes, sir.
So what is the maximum possible kinetic energy? How much you can get at most?
The Q value, sir.
So K max is Q value. And that is why the K max we write as H nu minus phi. And this is the possibility. This is the possibility. Is it reality? No.
No,
This is
sir.
the actual value. This is the maximum possible value. So in the Einstein photoelectric equation, the Ke max represents what is the maximum kinetic energy an electron, you can say a photoelectron can have. Understood?
Yes, sir.
So the photoelectron can have up to this value. This is the maximum possible value. It is not the value which you can expect all the time. Understood?
Yes, sir.
So if someone is writing K equals to H nu minus phi, this is wrong. Because this is not necessary condition, right?
Yes, sir.
But if someone is writing K max, this is right. Understood what is the difference between the two?
Yes, sir.
In the first equation, you are saying that kinetic energy will be this much, which is wrong. In the second, you are saying that the maximum possible value of kinetic energy is this much, which is correct. So
Yes, sir.
theoretically, the possibility can be predicted, right?
Yes, sir.
But the possibility cannot be the reality all the time, isn't it?
Yes, sir.
Okay. Now, as I said, imagine that an electron has ejected here. Because of the potential difference, the electron will accelerate, right?
Yes, sir.
And when this electron will reach near the anode, due to the acceleration or accelerating potential, the kinetic energy will increase by how much? E times V.
EV. Yes, sir.
So if I write cathode, anode, so kinetic energy near the cathode can be any value from 0 to H nu minus phi, right?
Yes, sir.
But kinetic energy of the photoelectrons near the anode will be how much?
Mhm.
0 plus EV. Understood?
Yes, sir.
So you have to remember that at anode things are not same. It is like this. So do you realize the difference?
Yes, sir.
Okay. So now we define the third term, which is called the stopping potential. And we write as Vs. So Vs is basically the negative potential, or you can say the reverse potential. Look at this diagram. Here, the moment electron leaves the cathode plate, even with zero energy, it can reach anode for sure, isn't it?
Yes, sir.
Because once you come out, the field will accelerate you there.
Yes, sir.
Okay. But what if I reverse the polarity? If I change the battery sign, then
Then it would
assuming
decelerate.
yeah, it will decelerate actually. So if
Yes, sir.
the electron will come out with no energy, it will come inside back. It will go back to the plate itself, right?
Yes, sir.
If it will come outside with some energy, and if that energy is less than EV, what will happen? It will never reach the anode, right?
Yes, sir.
Because to reach the anode, you have to overcome EV energy, isn't it?
Yes, sir.
So stopping potential is the minimum reverse potential that must be applied to stop the fastest moving electron
Mhm.
from reaching the anode. What does it mean?
So that means it is the potential applied to make any electron from not reaching the anode.
Correct. It means to stop the photocurrent.
Yes, sir.
So how to define this stopping potential? It is the minimum reverse potential required to stop the fastest moving electron from reaching the anode. Now, this is something interesting. It means the Ke max is roughly equals to EVS, but because it is failed to reach the anode, so it means it is slightly less than EVS, right?
Yes, sir.
Because if it is exactly equals to EVS, it means it will reach the anode and will stick to it. But we have to
Yes, sir.
prevent it, which means few nanometers away from the anode, it should stop. Which means the Ke max should be on the lesser side, right? Not on the
Yes,
equal
sir.
side. It is roughly equal. Numerically, we always check equal to solve question. But theoretically, theoretically, Ke max not should be Ke max will be slightly less than EVS, right?
Yes, sir.
Isn't it? And
Yes.
therefore, if I rewrite the same answer which I wrote earlier, so the kinetic energy, if I wish to write in terms of EVS, then I can say the K will be more than equals to 0, but it is less than EVS. I cannot write equals to EVS, right?
Yes, sir.
Because equal means you are hitting the anode, but we have to prevent the hitting the anode. So EVS is bigger than KE max. So the inequality will become, I mean, what we can call this is called. So less than equals to, it is like the closed interval becomes open interval. Understood?
Yes, sir.
So this change you have to be keep in mind. Okay, this is something very big thing. I mean, this part here and this part here is having difference. And most of the students, they fail to understand the difference, why we are writing this. Similarly, the EV, if I write EVS, kinetic energy will be less than, it cannot be equals to. So if I write EVS, then it is going to be value wise less than this value, right?
Yes, sir.
So KE max is not equals to EVS. It is on a lesser side theoretically, but for all numerical purpose, we can write equal. Okay.
Okay, sir.
So the Einstein and this was actually experiment was known to Planck long time back, but Planck was not able to explain this event. So it was Einstein who explained the reason behind this, you can say, experiment or its conclusion. And because of this, you can say, discovery of the reason he got the Nobel Prize in physics. So Einstein is known for the theory of relativity, but actually he was awarded with the Nobel Prize for the explanation of photoelectric effect, because he explained what happened. But the experiment was actually performed by Max Planck. Understood what I'm saying?
Yes, sir.
Okay. So the Einstein photoelectric effect can be rewritten as EVS equals to. So you can replace Ke max by equal, and of course, as I said, theoretically it is more, but we take equal when we write the equation to solve numericals.
Okay.
So you can write H nu
Sir,
equals to.
so if they ask a true or false statement,
Then you have to use theoretical answer.
okay, sir.
So when you replace Ke max by EVS, EVS is slightly bigger than Ke max. Okay.
Yes, sir.
And I hope the reason is obvious why I'm saying.
Yes, sir.
Now this is a simple equation and it can be written in variety of forms. You can write frequency equals to EVS by H plus phi by H, right? And if you plot a graph between the frequency versus voltage. The Vs is always on the negative side of the origin. Why? Because Vs is defined as the reverse potential, and Vs is here representing the numerical value. Okay.
Yes.
So if potential, if V is equals to Vs numerically on the negative side, you cannot get any current, right?
Yes.
Anyway, but if you're asked to plot the graph between the frequency versus voltage, and if it is Vs, okay, then it is a straight line with positive intercept, right? Can you
Yes.
see that? And it is something like this. Hmm?
Yes.
This is the intercept, this is the height. And if you extend the line, you can see when the Vs is touching some negative axis. So you can find the slope here. So slope is how much?
E by H.
So this value is how much? Let's say if I write minus V naught, this must be equals to how much? Correct?
Yes.
So this V naught voltage transfer how much?
Yes.
Understood? So you can see it will hit minus. So you may be asked some graphical question where you need to interpret the question. Just where whatever is the graph given to you. Let's say if you can see the y and x axis of the graph, try to write the Einstein question in that y and x and compare the intercept and slope to get the answer. Understood?
Yes.
So you may write like this. Then there are many ways in which you can write. So h nu equals to, you can write y plus a max threshold plus so I hope you can understand like all ways of writing this equation is obvious, right?
Yes.
So depending on the question, you have to convert the equation in a desirable format of y and x variable, and then try to compare things, you will get the answer. And also you will understand how to plot the graph. Okay.
Yes.
So let's say if I ask you that can you plot the graph of so how the graph look like if I ask you to plot? So which equation you want to use?
So HC by lambda is equal to 5 minus 1 second.
See, energy given minus work function is K max, right?
Yes, sir.
Energy you have given this much. Out of this energy, this is consumed in only coming out of this, the work function.
Yes, sir.
And the difference we call K max, right?
Yes, sir.
So one should not get confused. If you're getting confused, it's not good.
Uh, Sorry, sir.
So SC by lambda, now we are supposed to plot y versus x. Y is this much itself, so this is y. But 1 by lambda is x.
Yes, sir. So it would be a straight line.
So it must be a straight line with negative intercept and positive slope, right?
Yes, sir.
So it is something like this. And what this representing?
Mhm.
1 by lambda maximum.
Yes, sir.
So this is 1 by lambda max, because as lambda will grow, 1 by lambda will decrease. Which means beyond this point, there is no question of photoelectric emission, and hence the photoelectrons, hence the concept of kinetic energy. So beyond this, there is no graph. We can extend the graph by dotted line to represent the intercept value, which is -5. Isn't it?
Yes, sir.
So you will be asked to plot a graph in various things. Let's say if I ask you, can you plot the graph of Vs versus lambda? How it look like? Any guess?
So it will be like a hyperbola sort of.
Yeah, right. So if you plot the graph, now EVS is how much?
HC by lambda minus 5.
So you can see SC by E into X, 1 by X. Correct?
Yes,
So
sir.
this is like Y. Anyway, I hope you understood the graph meaning. And it is
Yes, sir.
definitely inverted. It's a parabola. And if I subtract something from parabola, it will shift up or down. So this is a regular parabola. Hyperbola, I mean not parabola. And
Hyperbola, sir. Yes, sir.
it is hyperbola. And if you put a minus sign, it means it will shift downward, right? Like this.
Yes, sir.
So we do not plot below the axis. We only plot up to the axis.
Okay, sir.
Which clearly means the graph should be something like this, with perfect intersection, and this is the lambda max, right?
Yes, sir.
And theoretically, if lambda will tend to 0, the energy becomes infinite, and that's why graph is also going to be asymptotic, right?
Yes, sir.
I hope the graph is clear.
Yes, sir.
So you can plot any graph which comes in the junction, because I mean the infinite graph you can plot. I mean quite a large number of graphs is possible. Let's say if you I ask you plot Vs versus frequency, plot how to look like.
So here it will be like a straight line.
Correct. So definitely if it is Vs versus frequency, so beyond, I mean, as the frequency is very small, it will not create any, and the intercept will be negative.
Yes, sir.
So this will be the graph, right?
Yes, sir.
Now, if you plot a graph, you can also check that slope is going to be constant or variable.
Sir, constant, sir.
And intercept will depend on what?
Sir, intercept for the x-axis or the y-axis.
The y-axis.
So then it will be like phi, sir, the threshold energy.
So if I use different metal, then phi will change.
Yes, sir.
But if I use the same metal, then phi remains same, right?
Yes, sir.
So you have to be very careful about the meaning of everything, intercept or whatever. And I think this is how much?
Minus phi by e.
Okay. So these kind of questions will be asked to you. Understood?
Okay, sir.
And you're supposed to answer. And for answering, you have to write the equation in that way as per the y and x variables, and you will get the answer. Okay.
Yes, sir.
Now we are good to go to the next concept, and that is called the saturation current. So this is the last theoretical concept. So the word intensity, if we define the general definition, the general definition of intensity and intensity in context of photoelectric effect are different as per NCERT syllabus. So if you are studying about the modern physics and the word intensity comes, so there the intensity refers to the word, the meaning photon intensity, not the energy intensity. So there is something called photon intensity, or it is more precisely called photon number intensity, is taken as intensity in context of photoelectric effect, which means the I here represents dN by dt per unit area, which means number of photons falling per unit area per unit time. Okay. So this is called the number intensity. Okay. And in case of photon intensity, we have something called power. So power is defined as the amount of energy per unit time, right?
Yes, sir.
And energy we know is number of photons into h nu, correct? Because
Yes,
one
sir.
photon will have h nu energy, so dn photon will have dn h nu energy, right?
Yes, sir.
And dn by dt we can write as I into a, right?
Yes, sir.
So we have something called energy intensity. And let's call this as IN, the number intensity. So there is a difference. I will just use this different notation. So energy intensity is defined as energy per unit area per unit time. And if you try to compare the two different types of intensity, you can see that this is power upon area, I mean area, and power itself is this much. So power upon area becomes how much?
INHD.
So intensity, energy intensity is number intensity into h. Okay. So sometimes they'll ask you how many photons are falling per unit time, or how many photons are emitted by the LED bulb. So if I give you a bulb, let's say we have LED bulb of power P. So in case of bulb, the power represents which intensity, photon or energy?
Mm,
So you can get to know through the dimension or the unit written there. So if I say the power of LED bulb is P watt,
so that means it's energy.
it
Oh,
is
no, no, no.
energy.
It is,
Yeah, yeah,
yes,
yeah, it is energy only. Because what means P joule per second, right?
yes, sir.
So what is the photon Pn? So you can just simply add Pn equals to P watt upon h nu. That's it. What is
So
Pn?
H nu is again energy.
Yeah, so that's why you're getting number, right? Dimensionless.
Yes, sir. So, but then per second is there.
Yeah, yeah. So of course, Pn is the number of photons emitted per second.
Yes, sir.
So if I give you a simple question like this, a red LED versus blue LED. And the power rating is same. So which LED is emitting more photons? So this you can also write as E what?
All right. So the LED is
So you can see the number is proportional to lambda.
yes, sir.
So bigger wavelength will have more number
So
power.
the red one. Yes, sir.
So red will emit more photons per second than blue,
Yes, sir.
because for the similar energy, the red will have less energy. So to compensate for the energy, it will emit more count of photons, right?
Yes, sir.
So these are simple questions that you can answer. So uh, En red will be is clear.
Yes, sir.
So you have to play with the different notation. Sometimes the In they write as small n. Okay. So and IE they write as I only, which is NH nu. Okay.
Yes, sir.
So we write energy intensity as number intensity into H nu. It's the same thing, but conventionally it is written this way. It doesn't matter how you write. So you have to actually understand from the question itself that which kind of symbolic notation they are using for a particular question. But these things are very
Okay.
easy to derive. If you know the basic, you can derive, right?
Yes, sir.
Okay. So now, because of 1:1 relation, so uh, because of 1:1 relation between photons and electrons, one electron can interact with only one photon at a time, right?
Yes, sir.
So if every photon is able to meet one electron exactly at the topmost layer of the surface, then the maximum photo electrons we can receive, achieve is equals to the number of photons falling per second, right?
Mhm. Yes, sir.
Assuming every photon is capable of emitting one electron. But if we define the quantum efficiency, so it is defined as number of photo electrons ejected So it doesn't matter if you either take the first two or all three or only first. So number of photoelectrons ejected per second per unit area upon number of uh, photons incident per second per unit area. Generally, quantum efficiency is a fixed quantity. So if you know the quantum efficiency and if you know the photon intensity, so if you know how many photons are incident per second, so eta is basically number of actual electrons which is coming out of surface upon how many photons are hitting per second per unit area, which is like in the numerator you can see I have used the subscript electron E and in the denominator I'm using the subscript P for photons. Okay.
Yes, sir.
Okay. And therefore so notational, okay, I can leave up to this point because you may be asked to find the amount of charge developed over a given time. Okay. So charge is how much? So if a metal surface will keep on emitting electrons, it will eventually develop some charge, right?
Yes, sir.
So if it is constant, then we can simply multiply with the area and time t, right?
Yes, sir.
Right. So this will become correct.
Yes, sir.
Uh, okay, like this. So I hope this is clear. Efficiency into number intensity is the charge, and then you can multiply with area into time. Okay. So you may be
Yes, sir.
asked to find the charge. Uh, okay. Imagine if I have a small point source of P watt, power is P, and away from its source there is a disk, a metallic disk.
Sir, can you just come back in a minute?
Okay.
So, sir, are you there? Okay, so
Okay. Imagine we have a disk of a radius r at a distance x from the source, right? So how much
yes,
power is received by the disk? And let's say it is emitting a monochromatic light of frequency in. So I n is how much? P in watt upon h nu, right?
yes, sir.
Now out of these many photons, how many photons will reach this disk? Tell me. Tell me.
Yes, sir, I'm applying the solid angle.
Hmm. If this is theta, then
So then, uh, out of the total part, 2 pi 1 minus cos theta will reach, yes, sir.
so out of number of photons emitted, all photons from this angle will reach there, right?
Yes, sir.
So in by 4 pi into
2 pi 1 minus cos theta.
so ion received okay. Now if this is the number of photons which you receive per second, okay, then how many photoelectrons will emit if the quantum efficiency is eta. Then I, number of photoelectrons ejected per second. So number of photoelectrons ejected per second is how much?
So mu in by 2 1 minus cos theta. Sorry, I mean n eta.
Okay. So charge on the disk will be how much?
Mm.
As a
So
function of time
I
t
times the e
into
into e
t.
sum. Okay, yes, sir.
Okay. So what is the electric field at the point of the source as a function of time t? It is similar to the formula of this, right?
Yes, sir.
So you can see that this may lead to a very challenging problem, right, in JEE-Mains. Okay.
Okay, sir.
Anyway, but we have now digressed from the actual topic. So we were trying to understand the concept of saturation current, right? What we
Yes, sir.
realized that how many electrons can be emitted by the surface of a metal per second? It is predetermined by the quantum efficiency, right? And
Yes, sir.
therefore, the current also kind of depends on the photon intensity, like how many photons are hitting the surface is eventually deciding the how much current we can create up to, which is the maximum value of current we can create. And that is why the word saturation, like what is the saturation value of current, how far the current can go to. So we have to go back to the experiment. So now what we need to understand that that as a result of photoelectric emission, now these photons are hitting the surface, and as a result, the electrons are emitting, right? So when the first bunch of photon will hit the plate, a bunch of electron will emit and will move towards the anode, right?
Yes, sir.
And meanwhile, other bunch will also come out. Meanwhile, other bunch will also come out, and therefore, the charge will start accumulating between the plate. And what will happen? The charge density will start growing between the plate. So eventually, the plate which was empty is now filled with charge everywhere. So eventually, this will happen. So this space will start, getting filled with charge, and the density will, of course, because it's made of electron, this electron density will have some repulsive power, and therefore you cannot keep on putting more and more photons into this space. A time will come when the density will become constant. Now, when the density becomes constant, what will happen? We cannot accommodate any extra electron in the given volume. Why it is so? Because of the the natural repulsion between the charges, correct?
Yes, sir.
So in such scenario, if 10 photons will hit, let's say quantum efficiency is 80%, then 8 electrons will eject. And they will try to enter the charge space, right?
Yes,
But to
sir.
keep the density constant, exactly 8 electrons will be absorbed at the anode plate. And therefore, as per the quantum efficiency, what we will see is a constant current in the emitter reading. So emitter will start showing the constant value, and it will be exactly same as per the quantum efficiency, how many charges are getting ejected from the plate. So that scenario we call saturation current. It's clear what is happening.
Yes, sir.
So what is saturation current? It is a condition in which the charge density between the plate becomes constant. Therefore, the total number of charge leaving the cathode is equal to total number of charge received at at anode. And this process will be without any delay. It means electron will come out and will be absorbed on the other end almost instantly. Is this clear what I'm saying?
Yes, sir.
And because the current is kind of limited by the photon number hitting the plate, So we call this as saturation current because we cannot exceed this current no matter how high the frequency may be, right?
Yes, sir.
Yeah, of course, if you start hitting more photons per second, if you increase the photon intensity, which is basically the photon number intensity, as I said earlier, then you can achieve a new saturation value, but you will always have saturation value. So In dictates the Is. Understood what I'm saying?
Yes, sir.
So in case of saturation current, the charge density between electrodes becomes constant. Therefore, the number of charge leaving the cathode per second is equals to so the saturation current we can always write as eta In E, right?
Yes, sir.
Eta is for efficiency, In for the number of photons hitting per second, and E is the charge on each electron, right? Now comes
Yes, sir.
the now comes the two or three important graphs that we should be aware of.
Sir, IN is for unit area also, right, sir? Like per unit area.
Yeah. So I have to multiply with area also.
Yes, sir.
Assuming both plates are identical. Okay.
Sir, and for the last question that we solved.
For this question,
Yes, sir. Sir, I'm a
so
bit confused about the use of IN.
why are you confused? Ion is what? PW represents what? Power in terms of energy, right?
Yes, sir.
So number of photons hitting per unit area per unit time. Okay. Okay, we are not supposed to take ion because the area is not there, right?
Yes, sir.
So we have to only count the number of photons, leaving the surface per unit time. So anyway, this is correct. So this is coming out of the surface, no matter what the surface. This is not the ion. This is actually the mistake. This is not ion. This is the total photons, right?
Yes, sir. So it should be like we are considering charge
Whatever.
emitting from a particle.
Yeah. So this is like something I into A. I mean, you can consider number of photons. That's a good question. Number of photons emitted per second. That's it. Let's call ion here.
Okay, sir.
Then in that context, it is clear. Okay.
Yes, sir.
Okay. Now, okay, you have to understand from the context only. There are certain graphs
Okay,
which
sir.
are very famous that we should be aware of. So the first graph is saturation current versus potential applied. So here, if I say that let's say if I want to draw, we have 3 plates. Let's say of identical area. All are receiving photons with the same count. So IP, not IN. It's IP. Yeah, IN is fine. The number intensity. So these are number of photons hitting per unit area per unit time, right?
Yes, sir.
All are receiving the same photons, as we can see.
Yes, sir.
Let's say we have the work function phi1 for this, phi2 for this, phi3 for this, and this is the order. Okay. Okay. So which plate will have the Ke max? So
Mm.
all are receiving
Sir,
uh,
the phi
same
one, sir.
frequency. Sorry. So they are having the same frequency, same intensity.
Yes, sir. So that
Similarly,
means phi one will be having the maximum.
kinetic energy, right?
Yes, sir.
So which one requires maximum stopping potential? The first one, right?
Yes, sir.
But all will eventually go to the same level of current because the number is fixed same, right?
Yes, sir.
So if you plot a graph, it will look like this. Because eventually they will have the same current, right?
Yes, sir.
But because of the different kinetic energy, they will have different stopping potential. And more the kinetic energy, more the stopping potential, right?
Yes, sir.
So this is the first graph that you should be aware of.
Yes. Sir, can you uh
Yes,
say
tell me.
nothing, sir?
The next graph, which is again very famous, is IS. Okay. And now, again, we have 3 plates. Uh, they are getting they have same work function, but they have just a minute. No, they also have same frequency, but they have different I value. IN1. So what will happen? In each case, the Ke max will be same or different.
Sir, K max will be the same.
So all will have the same stopping potential,
Yes, sir.
but because they have different count of photons falling over them, they have the same area. So which one will have the maximum saturation current?
Sir, here the first one.
So here the graph will start from one place. Not exactly like this. So these are the famous graph that one should be aware of. And this is the end of your photoelectric effect. You can solve any question as you wish. Okay.
Okay, sir.
So every question you have to interpret it accordingly. What is same, what is different, and you can easily realize that if all have the same stopping potential, it means they have same K max.
Frequency.
K max, not frequency. No, no. Only K. We can only guess K max because it is quite possible that first one is mu1 phi 1, and then you calculate the value h nu1 minus phi 1.
Yes, sir.
And it is quite possible that they may be equal, right?
Yes, sir.
Or they may not be equal. Let's say this is the case. Okay. So these two will have same Vs and it will have different value Vs dash, right?
Yes,
And
sir.
then depending on the value, I mean, you have to actually check. In J advanced, you have to check the h nu minus phi value to come to conclusion. So same
Okay.
frequency is not the criteria. What is the same? Stopping potential represents the same kinetic energy, right? The K
Yes, sir.
max value. Okay.
Yes, sir.
So these are the concept and questions of photoelectric effect, and I hope you can answer all of them with ease. It's not difficult. Okay.
Yes, sir.
So conceptually, I hope you are clear with the idea in photoelectric effect, how to deal with the theory and numericals.
Sir, the terminology for the photons intensity, you told that it varies from question to question.
No, no, no. In this, if they only use the word intensity, not the, they don't mention any unit. So from context, we'll come to know. And once you start reading the question, we'll come to know. If there is a confusion after that, also you can let me know.
Okay, sir. Yes, sir.
Okay. So try to solve all the PYQs previous year. And this is the basically dual nature of light and all. And in the short, I have tried to cover everything. And you may start solving numericals. Okay.
Okay, sir. Yes, sir.
So all right, we have done with the one. And